Good afternoon, this is Schweitzer. We're going to go through some answers to the kinetics remediation packet. The first part just shows some of the main concepts, right, which just shows it in multiple choice and written. All right, first piece here is our standard. How do atoms and molecules come together to form chemical reactions? This is commonly referred to as sort of reaction mechanisms. All right, so this section revolves around collision theory. Two substances will need to collide in a proper orientation. All right, so first problem says iron oxide is produced commonly used in hand warmers, which of the factors would would likely increase the rate of reaction. So we want to increase the collision theory. So the grind up, yes, um, yes, and adding a larger sample of iron, no. So this one here is increasing the actual collisions between, in this case, the iron and the air, Fe and air. This one is doing it by reducing activation energy by taking a different route. So it's not going a different route, it's taking a different pathway, and by lowering activation energy. All right. It says lacquer, otherwise known as nitrile cellulose, is a common plastic coating on everything from furniture to musical instruments. Sunlight is a common source of or reason the plastic coating will break down and become less effective. Statement: light is a catalyst speeding up the decomposition reaction. Justify or nullify this statement. Um, in this situation, it's probably going to be a nullify. All we're doing here is adding energy, and we really want to add something that doesn't just push something through a process, but really takes an alternate route around that process. All right, reaction mechanisms 5-2. All right, so here we go, slow and fast. So keep aware that we include everything that is in the slow step and before it. Key skills here is being able to identify the reaction intermediates. C is produced and consumed. That's an intermediate. And X is something that comes in and then is kicked out in the end. So this reaction is 2Y produces 2Z. The catalyst, sometimes listed above here, would be X. So given the reaction mechanism above, write the overall reaction. And we did that right there. Identify the catalyst, that would be X. What's the rate law of this thing? Okay, well, the rate law would be rate equals K concentration of Y squared. All right, next up. So given complete the energy diagram for the reaction above, it would be 2 steps. And the first one, it doesn't say whether it's exothermic or endothermic. So I'm going to do an exothermic graph. Just, oh, never mind, there's energy right here. Okay, so those are exothermic. The first one should be relatively slow. The second one's going to be relatively fast. The second one's relatively slow. So let's say like this, and then exothermic, and then like that, and then exothermic like that. All right, so we have our slow step is located right here. And that's the one that is going to be really slowing things down. This one goes pretty quick, but that's a slow one. If I want to speed up the reaction, speeding up anything prior to this step will do it. All right, 2 steps, 2 bumps. Next one, so it says students will be able to identify Reactions, okay, so this is, I can physically and mathematically track a chemical reaction. Okay, so the rate at which any substance appears, disappears from a chemical reaction is solely controlled by the Stoic ratio. So if I lose one of these, I'm also lose two of these, and I'll gain one of these, and it's a pretty standard situation, but we want to be able to do that, understand that. Okay, we have a chemical reaction here, but probably the next page. All right, so yep, given that chemical reaction, um, given that the rate of reaction, given the reaction above, a student measures the partial pressure of oxygen decreasing at a rate of 3 meters. This is a pressure, meters of mercury per minute. What's the rate of CO2 per minute? So let's do this. 3.0, and this will be of the O2, oxygen. Get rid of the oxygen and go to the CO2. Let's flip back to our chemical reaction, and let's see what we got. And that went the wrong way. All right, and I just copy and paste this, but we're getting rid of this and we're producing this. That's a 3:2 ratio. Perfect. All right, and get rid of the 3 and go to the 2. 2 times 3 is 6. 6 divided by 3 is just 2. So it's 2, it'd be Hg millimeters of Hg per minute. Okay. That's this guy right there. Okay, the method being burned, the methanol is being burned at a rate of 1.5 grams per second. What's the rate of water production? Okay, so we'll go this way. We have 1.5 grams per 1 second. Okay, 1.5. I want to get, this is of the methanol. I want to get rid of the methanol. And I want to go to the H2O. What's our ratio? Let's go back here again. Get rid of the 2 and go to 4. Okay, looks fine. 2 to 4 ratio. And for every 2 I consume, I produce 4. And this is just going to be double it. So 3.0 grams per second. There we go. And move along. Rate law and initial rate. The rate law and initial rate. So students will be able to run this rate law here and set this thing up in various ways. Keep in mind that this is the initial rate. That's important. The orders are important. Solving for K is important. Being able to get our units off of K is important for small points, and it matters. These are the number of items that are colliding in the rate determining steps. The effectiveness of collisions is the K value, no way of thinking that. All right, let's see what we got here. So what's the rate law for the following? So I have concentrations. This is a pretty standard situation. So I got single here. This guy is doubling, and this guy stays the same. So B is having no effect on the rate. So my rate law is going to be rate, and its initial rate equals K, concentration of A, over concentration times concentration of B. Only thing is I don't know my orders. And right now B is 0 orders. That's 0 going to be here. And then now it doesn't matter anything that this thing does. But I can take this guy here. It goes times 2. This is staying the same, but it wouldn't matter. It's not affecting us anyways. And this guy is going times 2. So it's first order. That's first order. And then if I want to figure out my actual K value, let's do that here. So I'm going to type in some information. Let's just go 1.0 e to the -4th equals K, concentration of A, 0.1 first, and B doesn't matter. So I'm going to divide out which is going to mean k equals 1.0 e to the negative third. And the units on this thing are just going to be, alright, so let's pay attention here for these units in case it's something you struggle with. It's going to be rate. I'm just going to divide out the concentration. It is A to the first equals K. So by dividing these two out, I get my units for this guy. Moles per liter, alright, moles per liter per, it's not giving me a time, let's just put seconds. So it's going to be molarity per second divided by molarity. And that's just 1 over seconds, or 1 over some unit of time. So 1 over seconds. Okay. And then, moving along here, determine the rate of disappearance of both A and B in the final. Okay, so all we gotta do is take and plug those concentrations in. Of course, B has nothing to do with it, but it's going to be the rate, okay, equals K 1.0 e to the negative third times concentration of A, which is 0.4, and to the first, and then we'll multiply out and get our rate. The rate is actually tracking the rate of B. Alright, so, alright, 0.4 times 1.0 e to the negative third is 0.0004. So that's my answer for B. So B equals 0.0004 moles per liter per unit of time. Let's just say seconds. Okay. And then I want to find this guy is half for that one. So A, it would just be a 2 to 1 ratio, is 0.0002 moles per liter per second for A. All right. All right. And that's it for that page. Next one, integrated rate laws. So just a couple of examples of everything. So now we got these formulas pretty important. I could see, typically speaking, that the first order, which deals with your typical half-lives, can always be very popular. Half-life. Okay, that's only first order. All right, so it says a first order reaction is represented by x going to y. The reaction is tracked as the concentration of x changes from 0.1 at sometime 0 and is at 0.205 at time 50. What's the value of the rate constant? Okay, so there's a couple of ways you can do this. Probably the most straightforward one would just be using the equation. Natural log of the concentration at times t equals negative k t plus the natural log of the concentration at time 0. Y equals mx plus b. This is where it crosses the 0 point. So plug our stuff in here. Okay, we have two concentrations. So natural log of 0.1, all right, equals negative k. That's what I want to find here. I don't have that. So k, and then I have t, time is 50 seconds. And then I have the natural plus the natural log of the concentration at time 0. All right, and then just go ahead and solve it out. Now this one here is 0.025. All right, so the natural log of, say, 0.1 is negative 0.23 minus the natural log of 0.025, and I got 1.38, and then I'm going to divide out by 50, and negative 50. So that would be negative 0.027. So in this case, K equals a negative 0.027. All right. Negative 0.027. And that would be 1 over seconds is my units. So that's all first order processes. Okay, and that is this guy right here. What is the concentration after 100 seconds? All right, so we can do this again, but now we have our unit here. It is a first order process, and you might notice some relationships here, but let's try it out. We have the natural log of concentration at times T, all right? Let's back this up 1 second here. And it says here that the concentration at time 0, okay, I got this backwards here. Let's back up here, sir. So I just fix this. All right, I want to make sure I get that right, so everyone's okay with this. This is times 0, concentration times 0. Well, my original 0, it's 0.1. All right, 0.1. And this one here is times 0 at this time. All right, oh, come on. All right, so now we got her. At times t, natural log of times t is 0.025, and this is natural log of 0.1. All right, now let's do this math again. All right, so the natural log of 0.025 equals negative 0.36 minus natural log of 0.1 equals negative 1.38. All right, so we have, in this case, negative 1.38, and then we're going to divide the 50 out, and divided by negative 50, divided by negative 50 equals 0.027. All right, K equals 0.027. That's 1 over seconds. All right, there we go. What's the concentration after 100 seconds? Okay, let's run this thing through. And again, my starting is the same. I want to have a different time, 100. Okay, and this is just a linear proportion. So if I'm up 50, now I'm up 100. So let's see what we get. Natural log of unknown value equals negative, all right, 0.027, and then 100 plus natural log of 0.1. Solve it all out, inverse natural log this thing. So we have negative 0.0277 times 100, and then plus the natural log of 0.1 equals, and that gives me 5, negative 5. I'll inverse log this thing, inverse natural log the previous answer, and I get 0.00625. 0.00625. And that's moles per liter. That looks like it should make sense. All right, what's the half-life of this thing? All right, so because it's first order, the time of 1/2 is equal to 0.693 divided by the K value. Now this is a shortcut method. I could just use the same formula and put in 0.1. So I could do this. The natural log of the concentration at 0.05 equals negative KT plus the natural log of 0.1. All right, and I could solve it all out. this would be 1/2. Okay, when you bring it over, natural log of 1/2. The natural log of 1/2 is, if you punch it in, natural log of 0.5 is 0.693, okay, which is what we have here. So in this situation, now we know K value, just going to solve it out. So the 0.693 divided by my K value, which is 0.027, equals, all right, 0.693 divided by 0.027 is going to give me 25.6. So about 25, a little more than 25 seconds. All right, 25.6 seconds is the half-life of this guy. All right, and that is going to be this guy right there. Write out the rate law for this reaction. Well, it's first order, so it's pretty simple to do. Rate equals K concentration of X. You can put a 1 up here, or you just leave it blank. What are the units of the rate constant? 1 over time. You could divide out, again, the molarity per time. I think it's in seconds. All right, that's that guy. Divide out X, which is molarity, and you get 1 over time. All right, what is the initial rate of the concentration if it's 0.1? This K value here is the same K value as this guy right there. So we'll do that. The rate equals 0.027 times the concentration of 0.1. And 0.1 times this guy is going to be, the rate equals 0.0027 moles per liter per second. And that's it right there. Okay, and then roll along. All right, how do half-lives work? Okay, half-lives only first order. The rate starts out fast and then and then gets slower as the process loses reactant. The rate constant and the half-lives do not change. So K value and the half-life, let's say it's 25 seconds, that's what we had earlier, that's not going to change. Well, if this stuff isn't changing and our stuff is dropping, that means the rate has to be dropping. So really be slowing down. Okay. Using integrate rate law, first order, you can derive the half-life equation is this. Okay. It says a 0.6 molar substance has a half-life of 10 seconds. What's the concentration for 30 seconds? Well, you should be able to take that 0.6 and say, okay, 10 seconds, it's going to 0.3. And then another 10 seconds, it's going to go to 0.15. In another 10 seconds, it's going to go to 0.075. And that is my 30 seconds. What's the rate constant of this reaction? All right, so 0.693 divided by 10 is going to be my new rate constant. And this thing is just going to be 0.693 divided by 10. All we got to do is move the decimal point. And it's going to get smaller. So 0.0693, 0.0693, that would be in seconds. Okay. And looks like we're done at that point. Thank you very much.